When you start thinking about network security as a beginner, it is natural to picture a single wall that keeps attackers out. But real networks are not protected by one wall, and real attackers do not stop at the first obstacle. A network security architecture is the intentional design of how systems connect, how traffic is allowed to flow, and where security controls sit, so they can reduce risk without breaking the business. The most useful way to design that architecture is to begin with a trust model, which is your set of assumptions about what can be trusted, what must be verified, and how trust changes as traffic moves through the environment. Once you have that trust model, you place controls in locations where they can enforce the model, observe important behavior, and limit damage when something goes wrong. For brand new learners, this can sound abstract, but you can treat it like designing a building. You decide which areas are public, which are private, how people can move between areas, and where you put locks, cameras, and guards so you are not relying on luck. A trust model is simply a structured way to answer a question that every network must answer whether it admits it or not, which is who and what is trusted and under what conditions. In older designs, a common assumption was that the internal network was trusted and the external network was untrusted, which led to a strong perimeter and weaker internal controls. That assumption can be dangerous because internal networks now include laptops that travel, cloud services that connect from anywhere, remote users, contractors, and devices that may already be compromised. Zero Trust, ZT, is a modern phrase you will hear that emphasizes not granting broad trust just because something is inside a network, but it is best understood as a mindset rather than a product. The mindset is that access should be granted based on verification and context, not on location, and that access should be limited to what is needed. Another trust model you will see is tiered trust, where some zones are higher trust because they contain critical assets and tighter controls, while other zones are lower trust because they face more uncertainty. Your architecture becomes coherent when the trust model is explicit, because then your control placement is purposeful instead of reactive. Once you decide how trust should work, the next step is to think about what needs protecting and why, because control placement without priorities turns into expensive guesswork. Every network has assets that matter more, either because they contain sensitive information, because they provide identity and access, or because they enable business-critical operations. Protecting those assets is not just about hiding them, because determined attackers can discover what they need, but about controlling the paths that lead to them and the permissions that allow them to be used. A beginner-friendly approach is to imagine the network as a set of neighborhoods connected by roads, and your job is to decide which roads exist, which vehicles are allowed, and where you check licenses. Some roads should not exist at all, because certain systems have no business talking to each other. Some roads should exist, but only under strict conditions, like authenticated and encrypted access. The trust model tells you which neighborhoods require the tightest checks, and it also tells you where you should assume that a compromised device might appear. When you treat access paths as design choices, rather than as accidental defaults, your architecture starts to reduce risk by design. Control placement is the practical art of deciding where to enforce decisions and where to observe behavior so you can detect problems early. Controls can be preventative, meaning they block or restrict traffic, or detective, meaning they record and alert on suspicious patterns, and good architectures typically use both. A common beginner misconception is that all controls belong at the perimeter, but perimeter controls only see what crosses the boundary, and many risky actions happen entirely inside. If an attacker compromises a single workstation, the next goal is often moving laterally to reach more valuable systems, and that lateral movement may never touch the perimeter. That is why internal segmentation, access control, and monitoring points matter, because they create friction and visibility inside the environment. Another misconception is that controls should be placed wherever they are easiest to deploy, but easy placement can create blind spots and inconsistent enforcement. Effective placement focuses on choke points, which are locations where many important flows pass, and on boundaries between trust zones, where verification should happen. When you view the network as a system of boundaries and flows, you can place controls where they do the most work with the least disruption. One of the clearest architectural patterns for beginners is the idea of zones, because zones translate trust assumptions into a layout you can reason about. A demilitarized zone, DMZ, is a classic example, where systems that must be reachable from the internet, such as public web services, are placed in a zone that is separated from the most sensitive internal systems. The goal is not to make the DMZ perfectly safe, because exposure will always create risk, but to contain the consequences if a public-facing system is compromised. Zones can be broader than just internet-facing versus internal, because you can design zones around sensitivity, function, and exposure. For example, a zone for user devices may be treated as lower trust because devices are frequently exposed to email and browsing risk, while a zone for identity services may be treated as high trust because compromise there can cascade everywhere. The value of zones is that they give you a map for where control boundaries should exist and what kinds of checks should occur at each boundary. When zones are defined clearly, policy becomes easier to implement because you are not making a unique decision for every connection. Instead, you are applying consistent rules based on the trust level of each zone. As networks become more dynamic, identity starts to replace location as the main way to decide what should be allowed, and that shift influences architecture strongly. Identity and access management, IAM, is the discipline of controlling who can access what, and it matters because it makes access decisions portable across networks, devices, and locations. If your trust model assumes that internal equals trusted, then identity checks might be weak internally. But if your model assumes that every access must be verified, then identity becomes central. For beginners, the practical implication is that network security architecture is not only about routers and firewalls, but also about integrating network decisions with identity decisions. When a user connects to a resource, you want to know which user it is, which device they are using, and whether the device meets expected security posture, because those factors change the risk of granting access. Network access control, NAC, is one approach you may hear about for checking device identity and posture before granting network access. But the high-level point is that the network can participate in verifying trust, not just forwarding packets. This identity-aware approach also supports least privilege, where users and systems get the smallest access needed for their role rather than broad network reach. When identity is integrated into control placement, the architecture becomes more precise and less dependent on static network boundaries. Encryption is another architectural decision that affects both trust and control placement, because it changes what intermediaries can observe and what they can safely assume. Transport layer security, TLS, is a common protocol used to encrypt traffic, and encryption is important because it protects data from being read or altered as it moves across networks. For beginners, encryption can seem like an automatic good, and it usually is, but it also creates design questions. If traffic is encrypted end-to-end, many security tools cannot inspect the contents without special arrangements, which can reduce visibility into malicious payloads. That does not mean you should avoid encryption, because unencrypted traffic creates obvious exposure, but it does mean you should plan where you need visibility and what kinds of signals you will rely on. Some architectures emphasize metadata and behavioral monitoring, such as destinations, timing, and volume, rather than content inspection. Others may place controls at endpoints where traffic is available before encryption or after decryption, which shifts monitoring to devices and applications. Thoughtful design also considers which connections truly need to be encrypted, which is often most of them, and how to manage certificates and trust in a way that does not create new weaknesses. The key beginner lesson is that encryption supports trust by protecting confidentiality and integrity, but it must be accounted for in how you place detection and inspection controls. Network security architecture also depends on understanding flows between applications, because modern systems are built from many components that talk to each other constantly. If you only think in terms of users browsing the web, you miss the reality that services call other services, databases respond to application servers, and automated processes move data on schedules. Good architecture begins with a clear idea of which systems need to communicate and which should not, because unnecessary connectivity increases attack surface. This is where segmentation becomes a control placement strategy, not a buzzword, because segmentation is the act of limiting which parts of the network can talk to which other parts. When segmentation is aligned to trust zones, you reduce lateral movement, which is one of the most common paths attackers use after an initial foothold. A beginner misunderstanding is to think that segmentation means making everything separate, but overly aggressive separation can break business processes and lead to emergency exceptions that undermine the design. A better mindset is purposeful connectivity, where each allowed path exists for a reason and is controlled with specific rules. This is also where understanding protocols matters, because controls are more effective when they limit not just who can connect, but what kinds of actions they can perform. When you design with application flows in mind, you place controls at the boundaries where those flows cross from lower trust to higher trust. Control placement is not only about blocking, because monitoring and visibility are equally architectural decisions, especially when your trust model assumes compromise is possible. Visibility means you can observe what is happening across key boundaries and within important zones, and that observation supports detection, investigation, and recovery. Centralized logging points, network sensors, and endpoint telemetry can all contribute. But the architectural question is where to collect signals so you can see meaningful events without drowning in noise. For example, monitoring at a boundary between user devices and sensitive servers can reveal suspicious access attempts, while monitoring at an internet egress point can reveal unusual outbound connections or data transfer patterns. Domain name system, DNS, logs can be particularly useful because many connections begin with name resolution, and unusual name lookups can hint at malicious infrastructure. But they must be interpreted carefully because normal applications also generate many lookups. For beginners, the main idea is that detection requires coverage, and coverage requires choosing vantage points where important activity is visible. If your architecture has many bypass paths, visibility becomes fragmented, and investigations become slow and uncertain. When you design paths deliberately, you can also design observation deliberately, which is one of the strongest benefits of architectural thinking. Another practical control placement concept is the idea of enforcement points that are close to the resource rather than far away, because proximity can reduce the blast radius of mistakes. If you enforce access only at the edge of the network, then once something is inside, it may have broad freedom, which conflicts with modern trust models. If you enforce access at the entrance to a sensitive service, you can apply rules that are specific to that service, such as only allowing the exact protocols and identities it requires. Access Control List, ACL, is a general term for a set of allow or deny rules, and you can find ACL concepts in many places, from network devices to application configurations. For beginners, what matters is not the specific technology, but the placement logic. Rules are most effective when they are applied where the decision has the most context. A service gateway, a database front door, or an internal boundary can enforce narrower permissions than a broad perimeter device that sees many unrelated flows. This approach also supports accountability, because you can tie access decisions to resource owners who understand what normal usage looks like. When enforcement is distributed across key points, the architecture becomes more resilient, because compromise of one boundary does not automatically grant access everywhere. Trust models also influence how you handle remote access and hybrid environments, where users and services connect from outside traditional network boundaries. Virtual Private Network, VPN, is a common approach for connecting remote users to internal networks, but from a trust model perspective, the key question is what level of access a remote connection grants. A beginner misconception is that once a user is on the VPN, they are effectively inside and should be treated as safe, but that can create risk if the user's device is compromised or if credentials are stolen. Modern designs often aim for more granular access, where remote users are connected only to the specific applications they need, and their access is continuously verified based on identity and device posture. This is not about making remote work difficult, but about aligning remote access with the same least privilege principles that should apply internally. Hybrid environments also include cloud services, where network boundaries are different and where identity and API-driven control often matter more than physical topology. For beginners, the takeaway is that architecture must reflect how people actually work, not how you wish they worked. When trust decisions follow identity and context, rather than assuming location equals trust, remote access becomes safer without becoming unusable. A well-designed architecture also plans for failure, because controls will sometimes fail, misconfigure, or be bypassed, and the question becomes whether the architecture limits damage or allows cascading impact. Resilience in network security architecture means having layers of protection, so that if one control misses something, another control can still slow or detect the threat. It also means building clear containment options, such as the ability to isolate a zone, restrict a compromised account, or cut off a suspicious pathway without shutting down the entire organization. Beginners sometimes equate resilience with adding more tools, but resilience is often more about clean separation, predictable pathways, and consistent enforcement. If every system can talk to every other system, a single compromise can spread quickly, and containment becomes a frantic attempt to build walls during a fire. If your architecture already has boundaries and choke points, containment can use those existing boundaries, which is calmer and faster. Resilience also includes recovery considerations, such as whether logs and evidence are centralized and protected so you can understand what happened even if some systems are wiped or rebuilt. When architecture is designed with failure in mind, the environment becomes harder to exploit and easier to restore, which is a practical goal for any trust model. As you evaluate trust models and decide where to place controls, it is important to remember that architecture should be understandable to the people who operate it, because complexity is itself a risk. If the design requires constant exceptions, if rules are inconsistent, or if nobody can explain why a path exists, the architecture will drift over time. Drift happens when teams make local changes to solve local problems without understanding the global design, and eventually the network becomes a patchwork of special cases. Beginners often think drift is inevitable, but good architecture reduces drift by making the simplest path the secure path. That means documenting intent in plain language, aligning zones to real system groupings, and ensuring that change processes consider how a modification affects trust boundaries. It also means designing for the organization's culture and operational capacity, because a design that requires perfect discipline will fail in a real environment. A sustainable architecture is one where controls are placed in a way that teams can maintain consistently, and where the reasons behind placement are clear enough that new team members can learn and uphold them. When sustainability is part of design, trust models remain meaningful rather than becoming slogans. Bringing these ideas together, building a network security architecture using trust models and control placement is about making your assumptions explicit and then turning those assumptions into enforced reality. You start by defining a trust model, whether it is a traditional perimeter mindset, a tiered trust approach, or AZT mindset that emphasizes continuous verification and least privilege. You then define zones and flows so that the network reflects what must be protected, what is exposed, and what is allowed to communicate for real business reasons. From there, you place controls at boundaries and choke points to enforce access decisions, and you place monitoring vantage points so you can see meaningful behavior and investigate quickly. You integrate identity and context so trust is based on who and what is connecting, not just where it seems to be coming from. And you account for encryption and remote access so visibility and security remain balanced. Finally, you design for resilience and sustainability so the architecture limits damage when something fails and remains understandable over time. For a brand new learner, the most important lesson is that good network security is not an accident of equipment, but the result of clear trust assumptions and smart placement of controls that makes secure behavior the default.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.